second derivative test. Right? Those are the two tests about this point. And they are about the same thing. These two concludes about the same thing about that point. And what are those? What's the conclusion of these two tests? Is about which property? What's that? Right. But there's one more word. Local, right? It's a local extrema. These two tests is about determining whether this is locally highest point or locally lowest point, right? That's the first derivative, and that's the second derivative. The conclusion is the same, but they use a different criteria. Sometimes this is easy, sometimes that's easy, right? Okay, so here is statement that is conveniently reformulated, more specified than the statement in the book. For example, like this, f double prime of c, and there's no other condition. F double prime of the book kind of assumes that the functions we are looking at here are very nice functions. So this is continuous and all that is assumed. So that is translated into following statement in there. If f prime of it's confused which one's which. Yeah. If f prime of c is a 0, and f double prime of c, not x, is greater than 0. That's the second derivative condition here, right? And I'm also assuming that not only at c, but around that value, f double prime of c, f double prime of x remain positive, which is guaranteed by the continuity condition on f double prime of c. So rather than deriving it, that's complicated. So this is a reasonable condition to put. At x equals c, derivative is 0, and at the second derivative at x equals c is a positive, and to the left or right a little bit, this f double prime of x remain positive. If that's the case on that interval, and fc remain as a local minimum. Okay, so we're not drawing a picture and prove that. We actually do mathematics, right? Use logic and algebra and theorem and deduce this is a local minimum, right? The picture cannot be accepted as a proof. So why does that work? Why does the second derivative test work? So that's what we're about to do. So that's the statement. Here's a proof of part A. I'm going to call that one, let's say it's part A. Part B is your exercise. So it's very similar. So you're going to pretend or mimic how the argument goes. If it is a local minimum in here, that is the lowest point. If you choose everything else, f of x, that f of x is always greater than or equal to that value, right? It's local minimum. So here's a point C there, and I found that, let's say that was B. And here is like a point that is a C plus 0.01. So slightly to the right, right? Here's a function value, f of c. And I found this value a little bit lower right here. That was a function value. Then is this f of c's local minimum? There's a lower value to the right? Is that a local minimum? It's definitely not a global minimum. Over the whole interval, there is a lower value. But is this two information, 2 points, necessarily imply that f of c is not a local minimum? Can this be still local minimum? How about this picture? Like that. Is that local minimum now? It is a local minimum, right? By looking at one point in here, that doesn't guarantee it is not a local minimum. It still could be a local minimum, right? So, but let's look at this statement. What we want to show is that everything we choose f of x, and then here, if you compare with f of c, this is supposed to be always smallest, right? This is always greater than or equal to, so that this is lowest. That's what we want to show. Suppose that's not the case, and this is a statement. Suppose that there is x such that is in that interval. C is contained in there. And it turns out you have to split this argument. I have to think about it a little bit. Let's say x is in between C and the B. C is somewhere in here, and B is the rightmost point. X is somewhere there. And one more condition is that f of x is less than f of c. See if that happens. Then use logic and theorem and see if something goes wrong, if something contradicting to each other. But then this statement is always true. This statement is always not true. So there isn't any value x in between c and b such that it's lower than f of c. That never happens. Therefore, for all the value f of x is greater than or equal to f of c. That proves to the right side it seems like a lowest point, and so on. All right. So this is we want to show that this is always not true, not just special case like this or anything like that. So here's first statement I'd like to pull out. By looking at f double prime of x being positive on that interval, what can you say about f prime of x? Increasing, thank you. Do you see that? This is one function, and its derivative is positive, right? So this is actually first derivative of the first derivative of f of x, right? So this relative derivative status is a first derivative. So what is the word again? Is increasing. Does that make sense? This function's derivative is positive, it's increasing. Okay? But we don't know f of x is increasing. It's just f prime of x is increasing. That's one thing we're going to use. Next thing is this mean value theorem again. Right? By mean value theorem, with the interval, we're going to apply mean value theorem to this c and x. That's the interval. C to x. Right? That's the interval we're applying the mean value theorem. Then what does the mean value theorem say? Something is equal to something, right? Left-hand side is the slope of a secant line. Right-hand side is the slope of tangent line. Remember that? So how is the slope of secant line formulated? F of something minus f of something, right? Remember that? This is the difference of y-coordinate and difference of x-coordinate. So what are those coordinates here? First slot? Right, but here we're applying that to c and x there, right? That's correct. So x minus c there, right? And x minus c there. That's the slope of what line? Secant line. On the right-hand side, slope of tangent line, right? And this existence of this value is not specified, but there is somewhere in actually interior of this interval. So I'm going to call this alpha. Where is this alpha located? In between what and what? The c and x. Not equal to c or x, is actually interior of the c and x. Okay, this is mean value theorem. And with this mean value theorem, we looked at the sign of the numerator and sign of the denominator. We had that problem before. So let's examine that part. From here, what do you think this x minus c, the sign of this one is? Is that positive or negative? It's a positive. X is greater, right? To the right, so it's positive. How about f of x minus f of c? Do you know this part? F of x minus f of c? Why is it going to be positive? Yeah, x is greater than c. Maybe then if you stick it at f of x, anything can happen, right? How do you know that's preserved? Not sure. The only condition that is listed between f of x and f of c is up there. What is it? Right, not equal to 0. That's correct. But there could be. It's greater than 0? Why is it greater than 0? Anyone else? F double prime of x is greater than 0. That's true. But what about between f of x and f of c? If you stare at here, there's no answer. It's somewhere else. First derivative is increasing, and then this implies concave up and down. Not this one is greater than. Only condition that's put on f of x and f of c is this one here. That was our supposition. There's one value f of x is actually lower than f of c, right? We assume that it happened. So f of x is smaller than f of c, right? So less than. That's our assumption. Suppose we have that x there. So now f prime of alpha, which is a quotient of these two things, right? F of x minus f of c divided by x minus c. That's negative divided by positive, right? What do we know about this one? It's a negative number. That's the conclusion that follows from mean value theorem. So here's a third item, is that it's between c and alpha that came in there. The c and alpha implies some relationship between f prime of c and f prime of alpha. So what do you know about f prime of something? F prime of something. What do we know about f prime? It's increasing, right? It's increasing. So if the input values in this order, here is a c, some value there, right? That is f prime of c, which is actually 0. Remember, we assumed f prime of c is 0. So actually it's down here. Now alpha is over here, right? Alpha is greater than that. Is that above and below? It's above there because we assume f prime of x is, we deduce f prime of x is increasing, right? So this value must be up there. So f prime of c must be less than f prime of alpha because it's increasing function in here. Since f prime of x is increasing. Fair enough? But what do we know about f prime of c? It was a critical point that we began with, right? So this one is 0. That was a hypothesis in there. Alright, so these are the three things. So does anybody find any contradiction? Something is not right if we deduce like this. It's about alpha. What do we know? What kind of property do we know about alpha? F prime of alpha here is greater than 0, right? But what was the conclusion before? Yeah, here is less than 0, right? So we have f prime of alpha less than 0 from second bullet item, and we have f prime of alpha greater than 0 from the third bullet item, right? That is not true. This can't happen, right? So what do? You go back and look at the statement, this is a supposition. If this happens, nonsense happens like this. The conclusion is that this never happens. Whenever this happens, there's a contradictory statement follows logically. Therefore, this never happened. There isn't any value in between c and b such that f of x is lower than f of c. That never happened. Everything, if this doesn't happen, what is it? F of x is greater than or equal to f of c, right? So that's kind of lowest point. For those values, that is to the right. Correct? So that's a contradiction. So I want you to stare at that statement and think about what the item B is going to be. What are we going to do in part B? We did this in part A. We suppose in part A there is x greater than c in between less than b such that function value is actually lower than f of c. What are you going to do in part B? Right, change the side. It was the right side, right? So you change to the left side. See if there is a x value that is smaller than c, still f of x is lower than f of c, right? We're looking for potential value that is lower than f of c. Then this is a problem, but we show that never happens, right? So here's exercise 1. Still in that context, is a part B of that part is a suppose prove that there cannot be x such that x is in between what and what, you think? B and C, we already did it, right? So C is on this side, right? You go to the other side of a C, and what is the lower value? That was A in the problem. And how about this one? Yeah, f of x. We want to see if there's still a value to the left side that is still less than 0. If it is so, that's a little problem. It doesn't necessarily again mean it's not a local minimum, but it's a potential problem. So we want to show this never happens. How do you prove this thing? Suppose there is x that satisfies all that, right? And follow through the 3 items. So proof goes like this. So I'm going to help you on that 3 bullet item thing. The first one is, first you suppose there is x such that x is in between a and c, and f of x at that function value is actually lower than f of c. Suppose that actually happened and something goes wrong. The first item is the same. This property f double prime of x being positive is not going to change, is the early hypothesis. And this implies what? F of x is increasing. Thank you. F of x is increasing. Second part was mean value theorem, right? So here's by mean value theorem. So which interval are we applying the mean value theorem to? Right, c is there. C got to be there. And x got to be there, right? So which is the correct order now? X to c, right? X is smaller. So we're applying mean value theorem to this interval, x to c. So this is tricky part. And the thirdly, this time let's use that beta in there. Remember we did alpha? Let's use beta this time. And that beta is in between x and c, remember? So there's this beta is less than c. There is this beta value by mean value theorem. And we think about what is the relationship between f prime of beta and f prime of c, and what goes here, the relationship operator. So these are rough outline, and I hope you find the contradiction at the end. Right? Try it. How was the mean value theorem side? Was that okay? I think it was, at least it's easy to write it up to here. That's standard that follows from the mean value theorem immediately. So mean value theorem on that interval. This is the last value of the interval and the beginning value of the interval. You put it in there. Somewhere in between f prime beta. You can state there. And we are doing, is this positive or is this negative? That's what we're doing. C is greater, right? Just right-hand value. So denominator is always positive. Numerator, this one comes from this condition again, right? This time f of c is on that side, even though it's still same inequality. So f of c is bigger than f of x. So if you subtract it, it's a positive. So positive divided by positive, that gives you positive slope of the tangent line there at beta. But if you use increasing property, beta is smaller than c, so f prime of beta must be less than f prime of c. So here is c, and the value of f prime of c, that's 0, and beta is here to the left. Then because it's increasing function, it must be down there. So it must be less than 0. Sorry about that. This should be less than 0, right? From there's a 0, it follows less than 0. So this is less than 0, this is greater than 0. They're contradicting to each other. So what do? You go back what we have supposed and conclude that this never happens. If there's ever happened like this, and there is this nonsense, therefore this cannot happen. If this never happened, that means that f of x is always greater than or equal to f of c, the other case. So to the left side of the value, to x equals c, f of x is always greater than or equal to c, and to the right side of the value, this can't happen, so f of x is always greater than or equal to c, right? F of c. So what does that prove? Everything is greater than or equal to f of c, right? Does that prove its local minimum? Yeah, because of that, therefore, for all x in that interval, a to b, to the left of c, to the right of c, f of x is always greater than or equal to f of c. That means f of c is the lowest value in that. It's local minimum. Make sense? Any question about the logic? Some detail? We can only theoretically approach this one because we assume something that cannot happen, and that you carry out the logic and run into a contradiction. So here is the second derivative test again. So did we prove both part?